let's start recording. Bring up the slideshow. Dun, dun. In case you're wondering, that was actually just right here. Okay. So, substance that is measured, that's the analyte, right? The quantity of the analyte to be measured is going to be the measurand. So that's what you measure out of the overall substance that's to be measured. That's actually what you distribute. Okay? All right. This was what we left off on. Okay, so analytes with equal concentrations are going to generally give different detector responses. The response must be measured for a known concentration of each analyte. This has a lot of reasons for it, but for example, let's say it's an electronic instrument. Just the electricity itself is going to add error into this. Okay. Does anybody know what an electrical outlet is in terms of voltage in the United States of America? It's called 120 nominal, meaning that it should be approximately 120. But in reality, they can range from 110 to 130 volts. And they have a frequency, actually, about 59 hertz that the electricity comes at. And so, for example, if you were to just go through these outlets and just watch them, they'd actually have rises and falls in the voltage. You just sit there watching. And so just the very fact that you're using a digital instrument will actually introduce error just from the electricity. Now, there are things you can do to clean the electricity, make it more standardized. Like, it's very expensive, and it doesn't always make as much effect as you would hope. Okay? But honestly, we have gotten pretty good at that because of computers, really. Computer power supplies are actually pretty good at it. So to determine the concentration of an unknown analyte, you're going to create what's called a calibration curve, or you sometimes hear it as standard curve. Okay, i.e. a curve using known standards. This is actually a graph. You'll graph the detector response as a function of the analyte concentration typically. And these will be your known standards that you'll graph first. These are what you fit with a calculation typically. And then you would then take unknown samples. So in this case, this is the unknown sample right here, sample number 9. Okay. And then your response from your instrument can go into this equation, and it will give you the amount of your analyte. Okay. There's more details and caveats to that, but this is the overall how experiments typically work. Okay. Anybody have any questions so far? No. Okay. Has anybody done this, Beer's Law? Back in Gen Chem? Okay. Maybe. All right. So to construct a calibration curve for ciprofloxacin, you'll use standard solutions containing known concentrations of pure ciprofloxacin. These are going to be prepared. They'll be injected into your column. Resulting peak areas will then be measured. You'll graph those peak areas versus those known standard concentrations here. And that will give you this graph. Okay. Now, please note that's very important what you put right here, that y-axis. Okay. And because there are responses you can get from instruments that are not linear. Okay. Peak height would very likely not be linear and not directly correlated to concentration. Okay. So if you were to sit there and just take peak heights and these things had different widths, you're actually going to get a different response. All right. And it very likely is just going to increase the error here. But there are other things you could do that would actually have different nonlinear responses here. Okay. Like intensity sometimes does not have linear responses, oftentimes. All right. So you'd really have to be careful. All right, so again, the area under each peak is going to be proportional to the quantity. Anybody that's taken organic chemistry probably remembers this, hopefully. Anybody that hasn't taken organic chemistry yet, you may not have heard this yet, but there you go. You have a leg up now. Okay. The graph of the peak area versus the concentration of each standard solution is then graphed. Straight line is drawn through, best fit. You will know to some degree your error because you can use an R squared. So that will tell you how well your line fits. Please note that these lines, these calibration lines, are almost always not set to be 0. So the y-intercept is never, is a strong word, but basically never, ever set to 0. Okay? Anybody know why? Yeah. Essentially the background. There can be noise or a little bit of response that is not actually your concentrations going up. It could be a contaminant in every sample, in which case this would tell you, hey, I have a standard problem that's in every single one of these samples that's the same amount of. Okay? And this lets you know that. If you set it to 0 every time, it'll show 0, but may not actually be the best fit, right? And you could have had something in your background that would have been triggering these. Something in your matrix, your surroundings that are triggering this. Okay? And so by setting that y-intercept to be able to move around, you can tell the difference. Right? This indicates that we probably have something that's not the ciprofloxacin that's reacting to some degree. Though, keep in mind, if you just have pure error here on certainty and not enough samples, this could be non-zero just from that. Okay? So this number, if it was pure random uncertainty, would go down to 0 as you add more and more points to this. Okay? If you add more and more points and this number stays very consistent, it's probably something that you're picking up that's an error in every single one of these. Okay? Okay, method validation. This proves suitability of the instrument and method. Make sure to follow written procedures very carefully. Make sure you question if you understand the written procedures. Double check. Keep easily understandable records, because if you do mess up, those records are going to allow you to figure out where you messed up, how you messed up, and every now and then that the written procedure is not actually suitable. Okay? You'd be surprised how often that one pops up, actually. So you're laughing like you've seen that. Yeah. Did you? It really does, right? Like, but that's why you check. That's why you have audits, right? Yeah. It happens. We're all humans, right? Even the person that wrote the method. So demonstrate reliable and reproducible results. Those are really kind of where new science happens, by the way, is where your standard procedures you followed for hundreds of experiments, and all of a sudden you start seeing differences. And you go, oh my goodness, we found something new. That's actually where a lot of that happens. But also it can be as simple as these written procedures. I've seen where people have stopped following a page because it got ripped out. Like it was points 1 through 9, and 9 was on a different page, and 9 got ripped out by accident, and now nobody's doing 9. Okay? Like, this is the reasons these things happen are so many, but this needs to demonstrate reliable and reproducible results, or else you need to change your procedures, right? So let's talk about interpreting results. The peak area observed in the chromatogram, should have really brought my water, can be converted into a solution concentration using calibration curves. Then the mass of the ciprofloxacin in the tablet can be determined using this equation right here. Does anybody recognize this equation, by the way? There's actually 2 equations technically. Anybody ever heard of M1V1 equals M2V2? You have a dilution, right? and then you have a mass conversion to that dilution. Yeah. So that's all that is you've taken a tablet, you've dissolved it, right? So you made a solution, massed the tablet, dissolved it in the volume of solution, right? And then you did a dilution. And that's all that is. Okay. And so have your mass of the tablet, mass of the dissolved stuff, volume, and the concentration, your cycloflaxin you got from that analyte curve. Okay. And that will give you the mass of cycloflaxin that's in the tablet. Notice we've done the conversion to upgrade it to the tablet mass because we only took a part of that, right? Anybody have any questions about that one? Okay. So let's look at Sarah's study right here. Now, this is kind of funny. I don't know if this person's name was actually Sarah, but almost every single thing that you will see in any of these PowerPoints or in your book are real, actual experiments. This book basically never gives you fake numbers. Many of them are from national data from the NIST. And so it's actually kind of a neat book, and I take a lot of examples from the book. They've actually provided with me with the actual figures, which is nice. That's why they look nice. Now, to be honest, my tables are sometimes messed up in this because every now and then they forget to replace the edited table that they put in the final book, and I don't have that one. So we may run across that. We'll see. I think I got them all fixed, but we'll see. Now, so Sarah's study here, 35 samples containing cycloflaxin. 2 tablets were suspect here. Notice they are considerably outside this range here, which is one of the things we'll talk about in statistics chapter of how do you figure out which ones are outside the range. Okay. But essentially, this is something like a standard deviation or 2 standard deviation band right here around this average. Okay. To confirm the results for sample number 9, 2 more solutions from remaining tablet powder were prepared. They were then analyzed using chromatography. Chromatography is just the way of saying the technique to produce chromatograms, which are individual ones of those spectra. Okay. The mean and standard deviation for those 3 measurements of the sample were reported. Standard deviation is going to be a measurement of reproducibility. Is it a measurement of accuracy? No. Not a measurement of accuracy, right? Because if you were enough off, you could be very tightly grouped, right? If your technique is off. But one of the things the standard deviations do is it does show you that they were very careful doing it, which does speak to, yeah, they may have been more accurate, but does not ensure accuracy. Okay. So Sarah's investigation here, standard deviation is actually 1% of the average. So this measurement right here was highly reproducible, right? 1% is actually very good standard deviation. Everybody realizes 1% is actually very good, right? Okay. Okay. Anybody have any questions so far? No? Let's talk about the general steps here. So these are some different rough comparisons of analytical methods here. Here we have gravimetry. Anybody know what gravimetry is? Balances. Okay. It's weighing things. The precision is typically within 0.1%. Selectivity is very poor because it really doesn't matter what you put on it, right? It's going to measure the mass. So selectivity very bad. It's pretty slow, usually. You can speed these other ones up with careful technique, but there's not really a lot you can do with gravimetric, right? Putting things on balances. It's just slow. Equipment cost is amazing. Absolutely amazing. It's why every teaching lab has a balance, right? And good balances. Yeah. Very, very cheap. Principal use, inorganic and really organic to some degree. But inorganic really, really benefits. Tiometry, this is precision, and you can see these, and I think you guys understand this well enough. You probably don't understand some of these methods, what they are, but you can Google them, and that bring it right out. Okay. More of these right here. Spectrophotometry is actually using light. It's the one where you use photons. Okay. Spectrometry is also another way of representing that, but it doesn't specifically call out light in that case. Okay. It could be other things you use, like shooting electrons at stuff. Okay. As long as it's a spectra. Anyways, I think you can see those, and it has selectivities, and it's a nice, actually really nice chart. If you're ever like trying to figure out what's the most cost-effective way to do things and what would be a good investment, this is a good place to sort of start. Okay, because it really has a nice structure to it. Okay, so these are the general steps in analytical process. You have number 1, formulating question. What do you notice about that already? What does that sound like? Scientific method, right? This is the scientific method. It's just been fleshed out more for analytical chemistry. Number 2, selecting the analytical procedure. Number 3 is sampling. The reason this goes directly into selecting analytical procedure is because in reality, your hypothesis, by the fact that you're doing analytical chemistry, is already somewhat subsumed in your question, isn't it? You're going to be finding how much of that is there. There you go. Is it there, and how much of it is there? Number 3, sampling. Number 4, preparing that sample. Most samples are going to require preparation, some very extensive preparation. Anybody taking biochemistry is going to really learn that. They have a lot of preparation for their samples. Number 5, validating the method. You'll notice that a lot of you that are doing like analytical type research with me, this is what we're going to spend a lot of time this next semester on, because none of these projects will have validated methods. So if you're doing research with me, most of these are going to need to be validated. Number 6 is analyzing that results. Number 7 is reporting and interpreting. Notice that reporting and interpreting are the exact same step, aren't they? Okay. What do you not do in science? What is absolutely not something in science? Interpreting, and then telling people the interpretation only. Right? That is not science, is it? No. Science is not your opinion. Science is disproving everything until you're left with something. Okay? And then trying to disprove that as well, right? All right. So you got to report all of this, and you can interpret while you're reporting, and you try to get other people going, hey, this would have been a better way of testing that. Hey, this is how you can disprove what you just said. Okay? And so the next one is drawing conclusions after you've done the reporting and interpreting with people challenging it. But is that the end? No. You really only stop on conclusions when you go, I can't really figure out any way of disproving this right now. So we're just going to have to conclude this here. Okay? And you report those. But if you figure out new ways, this should actually wrap all the way around back into the formulating a new question, right? And ideally, once you draw conclusions, it would wrap in around into new questions that are different questions, right? So it's a circular process that we grind away at the world until we get some sort of truths, right? Then we keep questioning those. All right. Okay, so formulating your question, this is going to translate general questions. You need to do specific questions that are going to be related to chemical measurement if we're talking about analytical chemistry, right? What's the most important thing about that question, though? Specific and testable. Okay? It needs to be something that you can actually test and disprove. Okay? Select the analytical procedure. So search chemical literature to find an appropriate procedure or devise a new procedure. I'm going to be honest, at this point in the universe and the history of humanity, there's actually not a lot of like questions that you won't find any analytical procedure that's pretty close. Realistically, if you haven't found a procedure that's pretty close to what you want to look at, it's very likely you just haven't looked very well. Okay. But devising new procedures or modifying those procedures or taking several procedures and then realizing, hey, these could be improved by combining these parts. Those are very, very, very necessary. Okay. And honestly, almost like I don't know of any procedures that I couldn't say couldn't be improved. It just is a matter of time and effort. And that's it. Okay. There is nothing that can't be improved right now. That's the sort of the place we are in science. And there will be new procedures completely that come along. They come along every year. So sampling, select representative material to analyze. Now, this is one of the places that you'll notice your book emphasizes this. I'm going to emphasize this. Anybody in the field is going to emphasize this, that this is probably the place where most people fail. Okay. Instrument manufacturers do a very good job of telling you after preparing sample and on. Okay. Like they have teams, they spend lots of money, they give you canned methodologies that work pretty good, and you can find lots and lots of methodologies. Okay. Sampling is usually the place you have to use the most brain power and you have to use the most imagination. Anybody that says that chemistry doesn't have imagination has never actually done any real science. Okay? Because you really have to like completely analyze the situation from one end to the next. All the way from that person is running around the world to your lab. Okay? And you have to figure out places where you're going to run into troubles and where you can introduce errors or eliminate errors, right? And so this is a big one. Remember, if you put in garbage, you're going to get garbage out. If you have bad samples coming in, there is nothing you can do. Okay? Bad enough samples, I don't care if you have $1 million instrument and you have the best lab in the world with 5, 10 Nobel laureates. If I give you a bad enough sample, you're just done. Okay? It's over. And interestingly enough, we went to a tour of Pace Analytics for everybody that didn't go on that tour last time. I'll arrange another tour this semester. And you may have noticed that they spend a lot of their time and attention on how samples are taken. And that's this issue right here, sampling. Okay? Because it's the one thing they can't control perfectly. Preparing the sample is the next part. This can be converting a representative sample into a form that's suitable for analysis. This could be dilutions. This could be concentrations. This could be binding to something. It's a very standard bindings. You know it better. There's many, many things that this could end up being. Very big thing in biological sciences. Okay. I can't think of any biological samples that don't have some sort of preparation that's necessary. Okay. So this can take a long time, by the way. I would say in some ways, this step right here might be the most time consuming of any of these steps. Okay. Actually, there's a wing of the Pace Analytics that does this preparing samples portion. And they have probably the biggest footprint. Yeah. And most people working there, if I had to guess. It's a big one. Number 5, validating the method. Check that the method reliably produces results that can answer the initial question. And this is one of the ways that like standard samples, where we talked about that calibration curve, that was validating the method. And so we would make a calibration curve, and then we take those samples, we'd rerun them versus the curve. Okay? Or at least one of them versus the curve. If we're really, phoning it in that day. Analyzing, you're going to measure the concentration of the analyte in several identical aliquots. Aliquots are portions of a sample. You probably have heard me use that numerous times in other classes. If you've had me before, I tend to just sort of slip it in my language. Okay, everybody want to say it with me? Aliquot. How many aliquots do you always measure? 7. Yeah. A minimum 3. Okay. Whatever your sample is, it's a portion of that sample. Yeah. So let's say you made up a 10 milliliter batch. You take like 1 milliliter aliquots for each test. Okay. So the uncertainty of the measurement is going to be very important, just as important as the measurement itself in analytical chemistry. Replicating measurements are absolutely essential because you can get completely off, totally messed up results if you do something once, right? I think everybody's had that lab where they just completely flub it, right? That's why you do it in several portions, right? Let me stress this, by the way, because it's something that I know that undergraduates, we don't really stress it enough. We give you a batch that's an aliquot. You run that batch, and so you run what you think is the full amount, right? Never run the full amount of anything, ever. Okay? Never. You don't run full amounts. Period. Ever. Was that clear? Okay. I did that myself. That's actually one of those things that I totally messed up. Can I say F word here? Anybody gonna be? Yeah? Not gonna tell me? Okay. I'm recording a video of myself doing it. So. I completely fucked that up. Like, my advisor was so pissed at me because I ran an entire sample of a $500 per milliliter. Yeah. And I was doing a reaction with fluorine, and it did not turn out very well. And we had to reorder it, and my advisor was pissed. Now, of the mistakes that were made by graduate students in labs, that's actually really small. Like, losing $500 is not actually that high. A lot better than the person that lost $10,000 salt windows because he dissolved them in water. But, I'm helping you avoid that mistake, okay? Okay. So, reporting and interpreting, you're going to deliver clearly written, complete reports of your results, highlighting any limitations. Be sure the report is appropriate for the intended audience. This is actually a really big one because your intended audience here now is always us, and we're PhDs in your subject. Your report for almost all of you is never going to be PhDs in chemistry or biology or whatever you're reporting again, unless you're working at like Mason Analytic, I guess. Your reports mostly are for scientists, but not always, right? Ultimately, those reports are going to be for business people, okay? And so keep that in mind. Are they going to know what an aliquot is? Heck no. Maybe if you're really lucky, but probably not, right? Hospitals are pretty bad about this, actually. And a lot of scientific organizations are actually really bad about this. They report these results in ways that their audience, target audience, has no ability to understand at all, right? You notice they are getting better. Your lab results that come for your blood tests have started highlighting things, probably. Okay. Better. Much better. All right, so drawing conclusions. So at times, your conclusions may point you towards starting over and reformulating your question. Very common. On methods that you've worked out over many, many times and are perfectly worked out, you still every now and then may go back into, I'm getting too many false positives. I'm rerunning these, and it's like 1 in 10 tests are giving me false positives. What do we need to do to fix that? Okay. There's some useful vocabulary here. There's species. This is going to be any element, compound, or ion that's of interest. You may end up doing an analytical test for multiple species at once. Okay, it's pretty common actually, especially for like HPLC. You almost always do that for multiple species at the same time. Interference. This is going to be a phenomenon in which the presence of one substance changes the response in the analysis of another substance. Also quite common, especially for ions that have the same charge. So many of the tests will be selective for charge on an ion. So if you have an ion with a 2+ charge, it will bind to all those places. Okay. Your bone marrow actually has a problem with this selectivity right here. And it has interference from strontium, actually, that binds into your bone marrow instead of calcium. So this is actually quite common. Masking. This is the process of adding a chemical substance to a sample to prevent one or more components from interfering in chemical analysis. We did masking back in organic chemistry, actually. You will almost certainly do masking and experience interference in biochemistry. And then we'll have some of those effects in analytical chemistry, of course, and we'll actually point it out. In the other classes, we don't point it out, and we just sort of give you a method to avoid that. And if you look and remember these terms, you'll see it. Okay? If you don't, the other people will never mention it. They're following a method that usually some analytical chemist made at some point, or they adapted from an analytical chemist at some point. Okay? Or somebody that effectively is an analytical chemist, but maybe is labeled something different. So this is constructing a representative sample. This is actually more challenging than you might think for certain substances. So for example, like a katana, testing katana or testing artwork pieces can actually be a lot more challenging than you imagine. Okay. So a random heterogeneous sample, your difference in composition is going to occur randomly and on a fine scale. So typically, if you just take large enough areas, and if you take multiple areas, it's going to avoid that. Okay. Random sample is collected by taking portions from an appropriate number of segments chosen at random. And if you choose enough at random, then the chance that you're going to have any statistical effect on your final result, very low. Okay. Biologists use these random samplings a lot, though not always to great success, because biologists have a tendency to not be random. To go, oh, that's a pretty thing. Oh, that one's cool. And go off and do those, right? In which case, not random, is it? Yeah. Segregated heterogeneous material. These are going to be large regions that have obviously different compositions. Has anybody ever seen Damascus steel or a painting, right? Those are great examples of this. Large sections, very different sections. And so what you need to do for those is make a composite sample. So this can be made of portions of each region with relative amounts proportional to the size of the region. So you take a little bit of this, about 20%. So you take about 20% of your sample from here. And then this part right here, about 66% of your sample. And then 14%. And this one's actually kind of a pain in the butt to do. But it can be done. Okay. Analysis is going to be meaningless unless you have collected sample properly. Garbage in, garbage out, right? Anybody know where garbage in, garbage out actually comes from? That's actually a programming one. Programmers are the ones that originally did that, because if you put garbage into a compiler, you get garbage out, right? You're going to ensure the reliability of the analytical method. Now, keep in mind that this is, in some ways, an SOP. It's an operating procedure, and it'll be self-reinforcing. So, for example, if you collect the sample improperly but ensure the reliability of the analytical method, it's a pretty good chance you're going to realize that you messed up. Okay? Because you're not going to get consistent results, right? Communicate results clearly and completely. Chemical analysis is the only middle portion of a process. It begins with a question, it ends with a conclusion. Everybody always focuses on the chemical analysis, and it's in many ways kind of the easiest part of it. That's been the best figured out for most methodologies. Okay. The other stuff is usually the ones that have the most likelihood of messing up, right? By the way, if you ever want to know sociology and where that has problems, that has sampling issues, and that has issues down here. Okay. So sampling and reporting / interpretation issues typically. All right, let's go on to the next one. We'll start chapter